Math 1314, Section IC1, Spring 2022, Tyler Junior College, Section 7.2, Polynomial Functions, Video 5, Multiplicities and X-Intercepts. In the previous video, we determined the X-intercepts of the following functions. F of x equals 2x times x minus 4 times x plus 3, and g of x equals 3 times x plus 2 times x minus 1 squared. Each of these factors produce an x-intercept, well, with the exception of one of them. In the first function, the factor of 2x produced the x-intercept of x equals 0. We got this by putting 2x equal to 0 and then solving. If you divide by 2, you get x equals 0. And we did the same thing for all of the factors. Well, almost all of them. For example, for x minus 4, if you put that equal to 0 and solve, you get x equals 4. And for x plus 3, if you put that equal to 0 and solve, you get x equals negative 3. Now, in the other function, the first factor was just a constant. It was just 3. And that didn't produce an x-intercept at all. It didn't produce an x-intercept because it doesn't have an x. In other words, what are you going to do if I say put 3 equal to 0 and solve it for x? Well, number one, it's not equal to 0, and number two, there's no x to solve for. So that didn't produce an x-intercept. However, x plus 2, when set equal to 0, gave us x equals negative 2, and x minus 1, when put equal to 0, gave us x equals 1. And we didn't really worry about the square, but I do want to remind you that we observed that the behavior at the x-intercepts was not always the same. Let's take a look at Desmos real quick just to remind ourselves what I mean. When we graph f of x equals 2x times x minus 4 times x plus 3, we got these three x-intercepts. And notice that the graph crosses the x-axis every time it hits one of those x-intercepts. However, in the other function, we had 3 times x plus 2 times x minus 1 squared. At least I think that's what it was. Let's go back and double check. That's what it was, 3 times x plus 2 times x minus 1 squared. And we noticed that at the x-intercepts, we didn't get the same behavior. At negative 2, we crossed the x-axis, but at 1, we touched it. And then we turned around and kept going and stayed above. Come back. So here's the summary of what happened. In the first function, we crossed at every x-intercept. In the second function, we crossed at one and touched at the other. Now, why is that? What features of the function can predict x-intercept behavior? Oops, you're not supposed to see that. Well, that kind of ruined a surprise, but that's okay. I'm not going to start the video over just to say, oop, can't see that yet, but now you can't. Still going to go into Desmos and we're going to figure it out. All right, so the real question is, why did the graph cross here at negative 2, but didn't cross at 1? It just touched the x-axis and turned around. Well, what's so special about the factor that produced 1 as an x-intercept? Well, it came from this factor. What's so special about it? It had a power. So you might start thinking that having a power on you has something to do with whether or not you'll cross the x-axis like we did at negative 2 versus touching the x-axis like we did at positive 1. Now we can test this theory. I'm going to remove this 3 to make the graph a little shorter. We can test this theory by putting some powers on these things. If we're correct, then putting a square on the x plus 2 should change the behavior right there at negative 2. And it did. By putting a power of 2 on the factor x plus 2, making it x plus 2 squared, then when we put this equal to 0 and solve it to get x equals negative 2, our graph actually touches instead of crosses at the x-axis. So does this mean that having a power causes you to touch the x-axis as opposed to cross the x-axis? Well, we can test that, but be careful. We're using the same powers on both of these. Maybe different powers do different things. Let's try raising this power to 3. Okay, we get a pretty weird graph that looks like an icicle, but notice that at negative 2, we're still touching the x-axis, but now at 1 we're crossing, yet both factors have powers. So why is it that a power of 2, which is on this factor, which gave this x-intercept, why is it a power of 2 causes it to touch the x-axis, but this power, a power of 3, on this factor, x minus 1, which created this x-intercept, 1, 0, why does that power cause it to cross? Now you might start thinking, is it because 2 is even and 3 is odd? Well, we could check that. If that is correct, then if I change that 3 to an even number, we should touch the x-axis at 1 again. Let's try changing the 3 to 4. And it happened. It's a little flat there, but that's the consequence of the power being so high. 4, it doesn't seem like a big number, but it is. At both -2 and 1, my graph is now touching the x-axis and turning around instead of crossing to the other side. And the powers on both were even. Let's make them both odd. We'll make this one, well, let me turn the graph off. Even powers seem to create x-intercepts that touch the x-axis. But what about odd powers? Let's make both of these 3s. If we're correct, then when I turn on the graph should cross at both -2 and +1 because the factors have odd powers, and they do. So it seems like, I wonder how low this gets. There it goes. It seems like the multiplicity, the power on the factor, has something to do with the x-intercept behavior, depending upon whether the multiplicity is odd or even. And that's what's underneath here. The power on the factor that produced the x-intercept. Oh, that's the answer to the question. What features of the function can predict x-intercept behavior? And the answer is the powers on the factors that produce the x-intercepts. These powers are called multiplicities. This is supposed to be pluralized. These powers are called multiplicities, the multiplicities of the zeros. So fancy new word, multiplicity. Multiplicity just means power on the factor that produced the 0 or produced the x-intercept. We've got it all summarized here. Oops, we already exported in Desmos. I thought the Desmos was a little bit early. Too late. But just to summarize here, in the first function, our zeros were at x equals 0, x equals 4, and x equals -3. And the powers on those factors, you don't see them because they are all implied first powers. So the powers on all these factors are 1s. And the x-intercept behavior on all of them was to cross. But on the second function, g of x equals 3 times x plus 2 times x minus 1 squared, our zeros were x equals -2 and x equals 1. But the powers were an implied 1 on the x plus 2 and an explicit 2 on the x minus 1. And the x-intercept behavior was it crossed at x equals -2 and it touched. It crossed at x equals -2 and touched at x equals 1. But the consistent thing is, and here comes the highlighting, when the power was 1 on the factor, we crossed the x-axis. However, when the power was 2, we touched the x-axis. And as we've already discovered in Desmos, because I jumped in there too early, even powers on factors will cause the graph to touch the x-axis. Odd powers on factors will cause the graph to cross the x-axis. So to summarize, how to determine x-intercept behavior? Each intercept, I should say each x-intercept, let's sneak that in there. It may invoke a line break. Maybe I can fix that. Okay, I can do it. I feel it. There we go. Each x-intercepts comes from a 0 of f of x. In other words, a solution to f of x equals 0. Each 0 comes from a factor, and that factor will always have a power, maybe just 1. That power is called the multiplicity of the zero. If the multiplicity of the zero is odd, if multiplicity is odd, the graph crosses the x-axis. If the multiplicity of the zero is even, the graph touches the x-axis. And I don't know why I have the word at in here. We'll take it out real quick. Why did that jump down? What is going on here? There we go. Seriously, what is going on here? I have no idea what's going on here. Pieces are going all over the place. It's just madness, I tell you, madness. Okay, is this better? All right, if the multiplicity of the zero is odd, the graph crosses the, and it still has the word at in there. Oh my gosh. That's the whole reason I jumped in there in the first place. Okay. If the multiplicity of the zero is odd, the graph crosses the x-axis. If the multiplicity of the zero is even, the graph touches the x-axis. Let's just take a look at a couple of quick examples. Find the x-intercepts, multiplicities, and x-intercept behavior. All right, remember, we're basically putting these equal to zero and solving. It's not critical to physically write equals zero, but this is what we're doing to get our x-intercepts. And when you put a factored function equal to zero, you just have to set each factor equal to zero. For h of x, let's start with 5x squared. We have 5x squared is equal to 0. If we divide by 5, we get x squared is equal to 0. And if we square root both sides, we get x is equal to 0. But what is the multiplicity? I'm just going to put mult for short. The multiplicity is the power on the factor. What's the power on the x? 2. That's even. And when the multiplicity is even, you touch the x-axis. The next factor, the next two factors are a lot easier. The next factor is x plus 3. And when you put x plus 3 is equal to 0, you can subtract 3 from both sides to get x equals -3. The multiplicity, mult for short, is the power on the factor. Do you see a power on this parentheses? No, because it's an implied 1, which means our multiplicity is 1. Now, 1 is odd. And when the multiplicity is odd, that means that you cross at, in this case, x equals -3. I'm going to back over here and put touch at x equals 2. And for the third one, let me move some of this over. See if I can grab all this. Move it all over. No, don't do that. Move it on over, please. Move it on over like George Thorogood. I don't know if any of you get that joke. It was kind of corny. There we go. Yeah. All right. Now, for the x minus 3, well, let's just get right to it. X minus 3, if we put that equal to 0, we get x equals 3. The multiplicity is also 1 because the implied power on the parentheses is 1, and 1 is odd. And when you are an odd function, when you're an odd multiplicity, that means you cross. So we cross at x equals 3. I'm going to put the results in the boxes, because it's these results that we're going to use as a means for sketching graphs. And I'm going to move the other function to the next page because there's not enough room to do that here. K of x equals x minus 4 to the 5th power times x plus 5 to the 6th power times x minus 11 to the 14th power. That 6 is looking a little janky. Just going to erase it real quick and redraw it. Should have done that before I unpaused. All right, so we're going to find the zeros, the multiplicities, the x-intercepts, and the x-intercept behavior, starting with the first factor, x minus 4 to the 5th. Now, when you set this equal to 0 and solve it, you temporarily ignore the exponent. We'll bring the exponent in just a second. If we solve x minus 4 equals 0, we get x equals 4. And notice that its multiplicity, the exponent, is 5, which is odd. And when you're odd, you cross the x-axis. So this would cross at x equals 4. We could go into Desmos, graph it, and verify that it will do that. I encourage you to give it a try. All right, next, we'll move to x plus 5 to the 6th power. Okay, that's supposed to be in black, no big deal. Again, we ignore the power just for a moment. We will discuss it when it comes time to talk about multiplicity. If we subtract 5 from both sides, we get x equals -5. The multiplicity of this 0 is the power, which is 6. That is even. And when your multiplicity is even, you touch the x-axis. In this case, we touch at x equals -5. Again, we can go into Desmos, sketch this function, and verify it. And you'll see that the graph touches at x equals -5. For the last one, x minus 11 to the 14th power. Again, we're putting this equal to 0, ignoring the exponent for a moment, and we get x equals 11. The multiplicity is the power on the factor, which is 14. That is even. And when you're even, you touch the x-axis at whatever your 0 was. It won't take but just a second to throw this into Desmos. So we're going to switch over to Desmos real quick to verify that what we predict is going to happen is actually going to happen, just on this last example, though. Okay, our last function was k of x is equal to, parentheses, x minus 4, close parentheses, raised to the 5th power, times x plus 5, close parentheses, raised to the 6th power, times x minus 11, close parentheses, raised to the 14th power. And we don't see a thing. We go to the home and we kind of see some stuff here. Now, I'll admit that these powers are kind of large, and so it's kind of hard to see what's going on. We see stuff all over the place here. I may have to manually adjust the viewing window so that we can see what we want to see. Now, our x's of interest are between -5 and 11. So I'm going to go into here and I'm just going to tell it to go between, we'll say -7 and 13. We want to overshoot it a little bit. And for the y-axis, because these powers are ridiculously large, our y values get ridiculously large. So let's take it from y to -100,000 to +100,000. And that might not even be enough to see the graph. All right, it's really hard to see what's going on here because of the size of these powers, so we may just look at them one at a time. But right here at 4, it's clearly crossing, and we predicted that it would cross at 4. The first box, we predicted it would touch at -5. Let's go back to -5 for a second, and we're going to zoom in on that. We're going to zoom in on -5 because it just looks like a stick or something, like it doesn't actually turn around. But if we were to zoom in enough on it, we'll see that the graph actually does. We got to zoom real close, go up, touch, and turn. In fact, it is so tight that we can't even tell right here that I'm at a different point. We're zoomed in so much, but we do have evidence that it touched the x-axis at -5, which is what we predicted here. And we also predicted it would touch at 11. So we're going to check out 11. Let's go back to the home view, scroll over here to 11. And it's a little more evident here that it touches and turns. We'll zoom in just a little bit to capture some of the curvature. Higher powers make for flatter graphs. It's so flat here. It's not really horizontal. It just looks that way. That's because the power of it is so ridiculously high. But we do touch and turn the x-axis. Touch the x-axis and turn at x equals 11 as we predicted here. So the key thing you need to know about multiplicities, let's turn me off here. The key thing you need to know about multiplicities is this page. Thought I stopped it there. Let's try it again.